Hi everybody. In this lecture we will discuss the infinite square well. It's a very interesting quantum mechanical problem. We will deal with the problem in one dimension for space dimensions. So the potential is a function, the potential energy is a function of the variable x. It doesn't change in time, so it's a static well. And in this case, we are doing a symmetric potential, all right? So for x lower than minus a over 2 or larger than a over 2 for the x variable, which is a space dimension here, the potential has a value of some u naught, all right? And inside a we'll call it a box. Inside the box of length a, so from here to here we have a total length of a. All right, inside the box here the potential vanishes. It is zero, so it is defined this way here. All right, it is zero for the modulus of x lower than or equal to a divided by 2. It is symmetric, and it is u naught for modulus of x bigger than or greater than a divided by 2. And we will make the value of u0 go to infinity, all right? For a finite value of u0, the problem gets a little trickier. The problem is more difficult to solve, and it leads to a transcendental equation for finding the eigenvalues of the problem. Also, it must be pointed out that for finite values of u0 for u or u naught lower than infinity for a finite value of the potential, there are a finite number of bounded states. All right, so we are dealing with problem concerning bound states. So let us make some definitions here, which are very important when you calculate the hydrogen atom, for instance, or any atomic orbitals, which is bound states. We are interested in bound states, right? And for bound states, there is an important property, which means the modulus of the function at the variable x going to infinity or plus minus infinity must vanish. The value must go asymptotically to zero for very large x. In 3 dimensions, for instance, 3D problems, we are considering, for instance, psi of the radius going to infinity, the modulus of the function must vanish. Usually you can define the energy so that the reference scale for bound states corresponds to negative energies and non-bounded states positive energies, but it depends on some constant. And in the case of the one-dimensional infinite square well, we will have bound states and we will define the energy so that the eigenvalues of the problem will be positive, all right? So this is very important. For infinite potential, you'll find infinite numbers of bound states. There are only bound states in the infinite square well, all right? But for finite well, for a finite well, you'll find a finite number of solutions corresponding to bound states. All right. By contrast, for an infinite square well, all the states are bounded, which means all the possible states of this problem satisfy this property, all right, which corresponds to the function going to zero at the infinity, all right. That's a very interesting issue in this case for an infinite square well. Also, the solutions are easy to calculate. So that's the main reason I will discuss here the infinite square well. But you can do the math for a finite square well. You'll find the transcendental equation for the eigenvalues, and you can compute it using a computer. It has a numerical solutions and always lead to a finite number of solutions corresponding to bounded states. And for energies above the well, above this value of u0, you'll find out non-bounded states or plane waves eventually. All right, but that's that's you can do as an exercise. All right, we'll discuss these topics here more or less qualitatively. All right. Well, first let us remember some of the classical physics. Right, so our problem is this. We have a potential energy here, which in our region of interest, potential is zero. So here inside the box, the potential is zero. And outside the box, or outside this region here, you have a potential which goes to infinity. So we are talking about perfectly rigid walls. There are two walls here, all right? So there are two walls, and the particle, if classical, can only, and quantum mechanically it will apply also in this case. Classically, if you put a particle here, it can exist only inside the box because it cannot transversely, it cannot cross to the infinite potential. Why is that? If we consider the total energy of a particle in classical physics, all right, it's a classical number here. I don't know if you can see in this color red what I'm writing. I hope so. So you have a p squared divided by twice the mass of the particle plus the potential energy, which is a function of x. This will be our Hamiltonian, and we will, when quantizing this problem, we will replace the values of momentum by an operator, of course. But in classical physics, you can remember momentum is mass times the velocity of the particle, and for a given energy of the particle, for any finite value of the energy, so energy lower than infinity, all right, lower than infinity. So for finite values of the energy, in this case, the particle, a classical particle, here you can calculate the kinetic energy. So in this case, or the velocity of the particle, and in this case, you have mv squared divided by 2 plus the potential, which is a function of x, and if you are trying to calculate here the velocity here, it's easy, all right? So the velocity here is just because the potential is zero here, the potential vanishes here. You'll find that the velocity here is just twice the mass times energy, and you can take the square root of that. So the velocity here inside the box, velocity can be easily calculated. So twice the energy divided by the mass of the particle, and you'll find the energy, because inside the box the potential is zero, but outside the velocity here can be easily calculated. So you just subtract the value of u0 here. You can subtract the value of potential energy, divide it by mass, multiply it by 2, and take the square root. So notice that for any value of energy lower than infinity, in the case of an infinite potential here, you'll find a complex value for velocity. It cannot be found any real value for velocity, and classically this doesn't make any sense. So in classical terms, if the energy, and you can use the same arguments for a finite potential. If your energy for bound states, all right, bound states also, in this case, bound states corresponds to energies lower than the potential barrier, all right? So for energies lower than the potential barrier, you could use a finite value here, right? Not going to infinity. And in this case, for energies of the particle lower than this value here, for energies lower than the top of the well, the U naught value, all right, you'll find out an imaginary value for velocity. It is not allowed classically, all right? So classically speaking, a particle having an energy lower than the potential barrier here, classically, velocity becomes imaginary and particle is forbidden to stay at any place such that the value of the position is in modulus greater than a divided by 2. So particle must exist here. But classically also, you can see this particle can have any value of energy, all right? So in one dimension, the particles can only live in a straight line, all right? So you have an infinite potential here, an infinite potential on the other side, so two perfect walls here, and the particle can live here in this line, in this unidimensional world. And classically, it can have any velocity here, so it goes to the right, to the left, it bounces off to the walls. It's reflected by the rigid walls, which are perfect walls, and it can have any possible velocity inside the box. All right. So this is classical world. But what we can expect in quantum mechanical calculations? All right. So just to summarize, bound states have energy lower than the potential barrier, the top of the well, right? The higher value of the well. And when you are considering an infinite value for U naught, all the states are bound states. All right. For finite wells, all right, for finite, you can find real velocities outside the box, and the particle can live there outside, all right? But for lower than U naught, for values of energy lower than this, the particle cannot leave the box. It must be inside the box, right? So this corresponds to bound states. Because in classical world, it's a certainty that you will find the particle inside the box. Quantum mechanically, perhaps there is a small probability of finding, but near the walls, for finite values of U naught, you can eventually find a particle traversing the wall. All right. So let us consider the problem quantum mechanically. All right. I will consider uh, for a finite value for U naught lower than infinity, so finite. We'll just briefly discuss what happens if you consider this kind of problem here. So for this is the x-axis here, the unidimensional axis. So this is u of x, considering that your potential is u naught for x greater than 0 and 0 here, and a particle described by quantum mechanics, all right, for the quantum mechanical description of a particle, you'll find that the Hamiltonian of the system corresponds to p squared divided by twice the mass plus some u0 value, all right? And this problem, when you calculate in terms of components and you are considering time-independent Schrödinger equation, or in this case, you are trying to find out what are the eigenvalues of your Hamiltonian problem, you are trying to find out the solutions of that equation, and this is u of x, right? And in this case, you are trying to calculate these kinds of differential equations. So some potential here, psi of x is equal to the energy times psi of x. This is just an eigenvalue problem, right? This is an eigenvalue and eigenvector problem. But notice that here in this region, for u lower than 0 in this region, you have so there is two regions. Region 1, for which u of x is 0. And in this case, your differential equation reduces to the following. Second order derivative, psi of x is equal to the energy psi of x. The energy of the particle is an eigenvalue, so you need to find out what the value is by solving the equation. So, but in this case, if you suppose you know what the eigenvalue is, and the eigenvalue is for energy lower than u0, right? This is what is our main interest here. You'll find here that the solution for this equation is some psi of x equals to some constant a times exponential of I, some wave number, times x, plus some b, the exponential of minus k times x. You can think about the solution here corresponding to some wave propagating forward, but when it collides with this wall, it gets reflected, and this corresponds to some amplitude A, this corresponds to some amplitude B, and traversing to the other side of this potential function here, you can consider some constant c, all right? And in this kind of problem, you need to equalize here, you need to match the functions in region 1. So this is the solution in region 1. And you will also have a region 2, all right? Where u of x is some constant u naught. And you are trying to calculate energies, the solution here with energies lower than u naught in this case. Of course, if you have greater than u naught energy values, you can have a wave propagating throughout all the space. But in this scenario here, where in region 2, which corresponds to modulus of x greater than 0, here this region corresponds to lower than 0. For x equals to 0, you have the discontinuity in the potential, all right? You'll find out the following equation: h bar divided by twice the mass, second order derivative of psi in the region 2, plus some constant u0 psi in the region 2 is equal to the same energy, because this is the eigenvalue of the equation, psi in the region 2. So you can move this u naught to the right hand side of the equation, but because the energy is lower than the u naught, the value in the right hand side will become negative, and it cancels out this negative, and your solution for this second region, you can show that, will be of the form psi 2 of x is equal to some c value exponential of alpha x plus some d value, so minus alpha x, some d value exponential of alpha x. And in this case here, k corresponds, the k value here corresponds to twice mass energy divided by the h bar squared, all right? So if you plug in the solution here, you'll find out the k squared here, the imaginary unit will become negative, it cancels out this negative value, so you can multiply twice the mass here divided by h squared and take the square root here, so the k value here corresponds to this thing, all right? And in this side, in the region 2 here, which corresponds where the potential is non-vanishing, you'll find that the alpha value is equal to square root of twice the mass, the u naught minus the energy of the particle divided by the h bar squared. All right? I don't know if you can see here what I'm writing. So I'll write it here, the alpha value here. The alpha value corresponds to the square root of twice the mass, u naught minus the energy divided by h squared. All right? And this value here will produce, since you can perform the math here, so what I'm trying to do here is put this term in the other side here. So you'll find this thing here, right? Eliminated from here. But since the energy is lower than u naught, this value is negative, you can just eliminate this negative here, just reversing the order here. All right, and you can plug in some solutions of this form. These are evanescent solutions, and you'll find out here, for the case of a finite wall, you'll find something like this. Right? There is a propagating wave, a counter propagating wave in the left side of this potential, but in the right hand side, since this term here grows exponentially and this decreases exponentially, and you are trying to find a solution in the infinity going to 0, this d factor here must be 0, and you'll find out something like this. Some wave here which decreases exponentially inside the wall. So classically speaking, if you have a particle here, it collides with the wall. If it has energies lower than u naught, it will be totally reflected, right? But in this case, you'll find out an evanescent wave crossing the barrier. And what? How can you calculate C, A, and all that? You need and B and values here. You need, of course, to equate. There are there are some conditions. You need to equate psi of 1 equal to psi 2. In this case, the boundary between the two regions is at x equal to 0. And also you need to equate, they must be equal, it's a boundary condition, the partial derivative, right? At the same point or at the same plane, if you are willing to consider that there are y and z axes and you are trying to find solutions which are independent of y and z, so it could be generalized to a three-dimensional problem, but considering one dimension, this is the point, x equals to 0, it's where the two regions are in contact. This is the interface between these two regions, and you need, of course, to make these two conditions match, all right? The function cannot be discontinuous at the interface, and the derivative of the function cannot be discontinuous at the interface. So you need to calculate these things here, all right? But it's a tremendous difference from the classical world, all right? In quantum mechanics, a particle has some probability of being found in a region where it is classically forbidden. But of course, if your potential goes to infinity, this u naught is too high, and this value of alpha, which is proportional to the square root of this difference, is also very huge, and the particle do not trespass to the other side. The wave function vanishes so quickly that is the same as considering that in the second region, the region 2, your exponential goes to 0. This value of d is equal to 0 because you cannot have a growing exponential to the other side. It's a physical condition, all right? And this c value, it doesn't matter because this exponential goes so fast, so rapidly to 0 that if u0, if or u naught tends to infinity, this alpha tends to infinity because it's calculated by square root twice the mass u naught minus the energy. For any finite energy, this goes to infinity in the limit divided by the h squared, and this exponential here goes much rapidly to 0 at the interface. Some infinitesimal value of x to the right makes this exponential go too fast to 0, and you can consider that in region 2, in this case, for if infinite barrier in the region 2, this solution goes rapidly fast enough to 0, and it can consider to be 0. It's a boundary condition for the case where the barrier is too high, all right? So let's return to our problem, which is the infinite square well. There are a lot of things to discuss here. Also, you can, but I'll let you research a little bit. You can Google it, but there are many analogies you can draw from optics. All right, if you insert between the interface between two materials with distinct refractive indices, you can insert a wave at a certain angle, which is a critical angle. If your medium from where the wave is coming, arriving at some interface, if this medium has a higher refractive index from the second medium, and you insert the wave at a critical angle or a higher angle than the critical, you'll have a total internal reflection. So the wave is totally reflected from the laws of classical optics or geometric optics. But an evanescent wave will cross the interface because Maxwell's equations demand boundary conditions to be satisfied. All right. So there are many analogies you can draw from this first problem, which we considered here from a potential U0 here and 0 there, and a particle described by quantum mechanics being reflected here, and they're having some evanescent wave. It's analogous to the problem, to some problems in optics, all right? But let's go back to our original problem, right? So the infinite square well, right? It's a quantum mechanical problem. We have this thing here. There are two perfect walls. Even quantum mechanically, if you have u naught in both sides, even quantum mechanically, you can think about some alpha value which corresponds to the rate at which the exponential vanishes, the alpha value here, because you have two interfaces here. At both interfaces, the value of u naught is the same, and the particle can move here. It can be reflected from the walls. But here you could think about the evanescent modes, and the alpha here would, which you'll find if you solve for a finite square well, all right? You will find something like this, and you need to find the eigenvalues of the energy, and this is what complicates a little bit because you will find out from boundary conditions matching the functions and the derivatives at this point, and at this point you'll find transcendental equations to be solved, all right? But the alpha will be given by something like this. And when the u naught is infinite, so u naught going to infinite, the alpha going to infinite, and the waves here are damped fast enough so that you can consider for an infinite square well a psi for x equal to plus or minus a over 2 and beyond, of course, right? And beyond. From that point, 0 always. But at the same point here, it goes fastly enough to 0, all right? So I don't know what happens here inside. We are trying to find out what will happen there, but the boundary condition is that the psi for x equals to plus or minus a divided by 2 go to 0, all right? So this is a bound state, and all the states are bounded between minus a over 2 and a over 2, all right? All the states in the infinite square well are bounded. Just because this alpha value here goes sufficiently rapid, makes the exponentials go sufficiently rapid to 0. So you find some terms depending on this thing here, and some terms depending on a plus here, because you're going to infinite to negative value of x, and the exponential must be damped, not growing. All right, so in this side you have a minus alpha x, and in this side plus alpha x, because going to the left you are going to negative value of x, and this exponential here must decrease, and going to the right alpha x must be, you already has you already have a negative value here. In this case the exponential will be quickly to zero, right? So that's it. Well, the problem now corresponds to the following. The function in region 2 and 3, I can call this region 2, this region 3. Region 1 is what really matters in this case, in the region of interest. So for modulus of x lower or equal than a of 2, the potential goes to 0, right? To be precise here, I have a discontinuity, but let us make the potential go to infinite, some infinitesimal values, or in this region here, infinitesimally displaced from a over 2. But that's a problem for mathematicians to worry about. For us, we are considering that in the region for x, modulus of x lower than or equal to a over 2, potential goes to 0, but the function at the boundaries must go to 0. Right? And the Hamiltonian here, we have this problem. The Hamiltonian applied to psi of x is equal to energy psi of x. And in this case, the Hamiltonian is just the kinetic term. All right? And we know this is just second order derivatives. All right? This is it. That's what we need to calculate here. All right? This is the problem. Well, you can think about a Hamiltonian being applied to some psi equals to energy to some psi, some eigenfunction here, which we are willing to calculate. This is a matrix. But when you project out this matrix to the position basis, this is the eigenvalue, so it commutes with this bra here, and this is the function psi of x, which is equal here to the minus h bar, second order derivative, divided by twice the mass applied to psi of x. This is what we can find. Why is that? You can project, you can include the completeness here and do the math. I'll skip that part, but if you are in doubt, you can find out the calculations elsewhere, and I also recommend Sakurai for just demonstrating. We already demonstrated that the momentum operator, when you quantize a theory, and this is just one dimensional, so this is just the derivative with respect to the x direction. All right, so in our case you can just replace this operator, and you just have this function here. All right, but now the solution for that differential equation, you can rewrite the equation this way. Look at that. The Hamiltonian minus h bar over twice the mass, second order derivative of the function psi of x is equal to the energy psi of x. What are you trying to calculate? This psi of this energy and these values of psi of x. You can just rewrite it in the following way: minus twice the mass times the energy divided by h bar squared psi of x, and this you can call minus some k squared value psi of x, and therefore your k value corresponds to twice the mass, square root of that, twice mass, the energy divided by this square root of Planck's constant. All right. And this kind of equation we already encountered many times in physics and engineering, and the solution can be written two ways. All right. You can write it as two complex exponentials, or you can write as two trigonometric functions. So I'll write this form here because it's more interesting for us right now. And this is A cosine of kx plus B sine of kx. All right, this is the form which I am interested in. Yeah? There is a reason for that. Also, you could write, of course, you could write the solution the following way. You could write solution this way here. Some constant C1 or A1, distinct from that, all right, and distinct from this B here, but some A1 exponential of I times Kx plus some B1 e to the minus I Kx. All right, you could write the solution that way, and after doing all the math, you find out the same results. No problem in that. But this is more appropriate for now, all right? This is more appropriate for now, okay? So I will not use this convention here because, of course, you could write the plus minus exponential to the I kx is equal to cosine plus or minus I the sine, and you can find out the relations between these constants a1 and b1 to the constants a and b, and of course this can be put in the form of a cosine plus b sine of kx. All right, so just a matter of personal taste perhaps, but in this case this form is more appropriate for reasons which we will see. All right, and we have written the potential in a symmetric form. This is very important, and this is the reason why I am using this form for the solution of the equation. All right, why is that? Notice that if you are trying to solve the following Hamiltonian equation, which by the way results in some equation of this form, we are dealing with a one-dimensional problem, but eventually you are trying to solve in more dimensions, and it helps a lot to find out the symmetries of the problem. So in this case, you have this thing here plus u of x psi of x is equal to the energy psi of x. So this part of the operator, the kinetic energy, is even if you, so let us just consider a little bit of the symmetries of the problem. Symmetries of the Hamiltonian in this particular case here. So the symmetries of the Hamiltonian, all right? This form, the symmetries of the Hamiltonian form to form a group, which is called the group of the Hamiltonian, which is a set of transformations you can apply to the Hamiltonian and put the Hamiltonian in the same way. So in this case, notice that you can replace x by minus x, right? You can change x by minus x. This is called the parity operation. Or, because you are considering just one dimension and all that, you can call space inversion. It is the same as space or spatial inversion. All right? I'll call it P. The operator is P. Right? P applied to something. Let me erase this side of the board here. When it operates on some function, it just produces some, in general, phase factor, but I'll introduce a plus or minus here, the function of minus x. So it changes x to minus x. It inverts the position operator. All right? Sorry. Kinetic terms, which corresponds to momentum, if you consider classical mechanics, it corresponds to mass, the time derivative of position squared divided by 2, it's just mv squared divided by 2. And of course, if you plug in minus x, it is squared here. So the kinetic term is symmetric under parity, all right? It does not change sign, right? So kinetic term is valid in quantum mechanics also for an operator form, is invariant or invariant under this operator, this P operator, this parity operator. If you apply the parity operator, you must change x by minus x, but the kinetic term is just the same value, all right? It doesn't change sign. While the potential, in our case, it can reverse sign eventually depending on the problem. So it's not invariant under parity. But in this case, our scenario here, in our problem, because we symmetrized u of x is equal to u of minus x. All right? It is easy to see that because it's just some function like this. X, u of x, it has the same value, u naught, both sides, it is symmetrized. So if you change some value of x by some minus x, the potential here is equal to potential in the other side. The potential for some x here is 0 and here also 0. Minus a over 2 plus a minus a over 2 plus a over 2, same value for the potential. For some minus x here and some x here, the potential is the same. So our Hamiltonian, in this case, the way we written the potential, we defined the potential, the parity applies. So in our problem, u of x is invariant under parity, right? So in this case, right, our Hamiltonian, full Hamiltonian, because it's just the sum of the kinetic plus the potential energy terms. Both terms are invariant, so our Hamiltonian is invariant under parity, all right? In this case, we can say that parity applied to the Hamiltonian, this way it's written in matrix transformation, so you write the following way here, is equal to the Hamiltonian. For matrices, when you apply to a vector the operator to a matrix, you need to apply the operator and the inverse of the operator in the other side. But in this case, the operator gives you the same Hamiltonian there. And if you consider Schrödinger's equation here, you can apply the parity both sides, but the parity operator commutes with the eigenvalue here. So you write this way here. So this is a transformed function. And the Hamiltonian for doing the math here, you can insert some matrix form here as the inverse times the matrix form, which is just the identity here times the function. And notice this is the same as h. And this is the transformed function, which is psi of minus x, and is equal to the energy psi of minus x. So the function transformed has the same eigenvalue. It also satisfies the Hamiltonian, and it must be an eigenstate of parity. So if it's an eigenstate of parity, it can only change sign. All right? So the parity operator operating to psi of x must be just one of these possibilities. Right? Plus or minus psi of minus x. Right? Because if you change sign, both sides, it doesn't alter the equation. Of course, you could find a phase factor or common phase factor also, all right? But in this case, just consider this possibility. The parity operator operating to the function just inserts a sign plus or minus, all right? And why is that? Because our solution here corresponds to two possibilities. A cosine function which doesn't change sign if you plug in minus x in place of x because it's an even function, and the sine function which is odd under parity because if you replace minus x here, the sine function changes sign. So remember, sine of some function of x is minus the sine function of minus x, and the cosine function of x is equal to the cosine of minus x. So the sine and the cosine function are parity eigenstates. All right? That's very important issue here. Well, this way we already know what to do. But notice that if A and B are both simultaneously non-vanishing, this function will not be an eigenstate of parity operator. So our functions must be at the same time the eigenvector of the Hamiltonian and an eigenstate of parity in this problem, because parity is a symmetry of the problem. And in this way, the solution must be of the form even solutions with A some value and B equal to 0. So there are even solutions. And the other possibility is A equal to 0 and B distinct from 0, which are the odd solutions. So there are even and odd solutions. Okay? There are even and odd solutions to this problem. But let us calculate the boundary condition. All right? So for k equals to the square root of twice the mass times the energy divided by the h squared, our solution is of the form it satisfies this equation. Second order derivative with respect to x is equal to this k squared minus k squared, the same function. In general, it admits a sum of two terms, but because of parity of the Hamiltonian, only cosine or only sine for each value of the possible case will be possible in this case. So look at what happens. We need to find that psi calculated at plus or minus a over 2 equal 0 because the potential is infinite. All right, so this is a boundary condition, and in this case, let us see what happens. So psi of plus or minus a over 2 is equal to a cosine of plus or minus k a over 2 plus b sine k plus or minus a over 2. And this way we can rewrite the solution because the cosine is even function, cosine of ka over 2 plus or minus, depending on what point we are considering, x equals to a over 2 or minus a over 2. These are the 2 points where the solution must vanish. So the solution must exist only inside the box, and outside the box solution must vanish, starting from a divided by 2 or minus a divided by 2. And because the sign is an odd function, these 2 points have opposite signs. And now look at the following property. You need to make this equation vanish. Because of the symmetry of the problem, we have a cosine function which is even, a sine function which is odd, and this equation implies that the wave function is 0 at x equals to minus a over 2 or x equals to plus a over 2 divided by 2, all right? Well, it is a property of the trigonometric functions, the cosine and the sine functions, that when one of them is 0, the other cannot be 0. It's impossible to find both simultaneously 0 at the same point. All right? This way, how can you solve this equation? If you plug in a and b distinct from 0, and you make a cosine equals to 0, the sine is not 0. It does not vanish. But if you make the sine equals to 0, the sine function equals to 0, the cosine will not be 0. They cannot be simultaneously 0. So you have a choice to make. A is 0 and b distinct from 0, then you can, no matter the value of the cosine, you can make it vanish, the sine function vanish, or you can choose b equal to 0, a distinct from 0, and then no matter the value of sine, the cosine must be 0, right? There are two choices to be made. So the even solution b equals 0. Why is that? Because the sine function, the sine of kx, is odd, so I need to make b equal to 0. I want even solution, all right? This way, a cannot be 0. Why is that? Because if in the solution you find a and b equals to 0, what is the probability of finding particle inside the box? 0. There are no particles inside. So if you want one particle inside the box, you need to make or A or B different from zero. Both cannot vanish, because if both vanishes, both constants are zero, your solution is just there are no particles inside. The probability of finding something there is zero. All right, so you want to find solutions with particles, with one particle there. So in this case, A must be distinct from zero, and the cosine, because B is zero, this term I will not worry about sine function here. But if A is different from zero, the cosine function of K A over 2 must be zero. All right, this is what the boundary condition tells us. All right, and the cosine is zero. The cosine can be made zero for multiples of pi over 2. Right, so the Ka over 2 must be multiples of pi over 2. What multiples? I'll call it n. All right, I'll call n. What what are these integer values? 1, 3, 5, 7, and all that. All right, so odd numbers. It's a weird thing what happens here, because for even solutions you need to find odd integers. All right, but it's just the way we defined the problem. All right, so if you have cosine of n pi over 2, it is 0. So these two numbers must be equal, and in this way I can call a kn, k subindex n, which is an integer number, is equal to I want to calculate the k value, so it's n times pi divided by a. All right, this is the solution here, which we are trying to calculate. So this is a very important property of quantum mechanics. You cannot have any possibility for k. The k values are quantized. There are a discrete number of solutions. This is to be compared with the case of a string with two fixed ends. There are modes of vibration, and this corresponds to the modes of analogous to the modes of vibrations. Also, for the propagating of electromagnetic waves, if you consider a metallic waveguide, you will find out that the electric field must vanish at the walls, the metallic walls, and in this case also you need to find some boundary conditions, and you'll find that not every possibility for the wave numbers there are allowed. Not all values are allowed there, and you'll find some discrete solutions. And these discrete solutions corresponds to some kn. In this case, for the even solution is n pi over a. All right. Just write down on paper if you want. We will discuss the odd solutions. All right. So for odd solutions here, odd, what we have to do, reverse the things which we are making zero. So b is distinct from zero. No matter what happens to the cosine, I need to make a equal to zero, because now if I have b distinct from zero, this sine function must be zero. The cosine cannot be zero, so the a must be zero. All right. And now plus or minus, which corresponds to sine function of Ka over 2, must be 0. This function sine of Ka over 2 is 0 only for the following possibilities. Ka over 2 must be a multiple, I'll call it some n here, a multiple of pi, all right? Some multiple of pi. These n values here for the odd functions can be 1, 2, 3, 4, 5, but now I can plug in this, I can multiply everything by 2, so twice n, and this factor cancels out. Now I can find the k twice n, all right, corresponds to twice the pi divided by a. These n values would be 1, 2, 3, 4, 5, and all that, but when you multiply it by twice, you will find the twice the n value, which I'll call n primed, is 2, 4, 6, 8, and all that. So you'll find the k n primed, which corresponds to the odd solutions, are n primed pi over 2. Notice that now I can drop out the prime and use a single over a here, right? A single variable, just n, and the odd values of the integers n corresponds to even solutions, and the even values of this integer n corresponds to the odd solutions. That's weird, but that's what we found. All right, and in this way I'll have the following: even solutions psi n of x for a given n, and for even solutions are 1, 3, 5, 7, they are odd numbers, corresponds to some normalizing constant, which you can find as an exercise cosine function of n pi x divided by a. All right, and the energies here corresponds to n. Remember, k is equal to the square root of twice the mass energy divided by the h bar squared. So for a given n, you'll find an n energy, and this energy here will correspond to h bar squared kn squared divided by twice the mass. And now you have found that h bar, this kn here, must be n pi over a. So you find out h bar squared pi squared divided by twice the mass a squared, right? This is a constant of the potential of the well, right? Times n squared. And this thing here, no matter what, for even or odd solution, is the same thing. So you have an energy scale here, E naught, some energy scale, which is defined by the mass of the particle and the length, the size of the square, the well, all right, times n squared. Notice that the energy values grows with the square of n, all right? So these are the even solutions, and the odd solutions are the following: some Bn constants, which must be calculated from normalization, sine of n pi x over a. These are the solutions. And these n are 2, 4, 6, 8, 10, even n values. All right, so this is it for a potential well, for a square well in this case. All right, the energies goes in this way. All right, and normalization implies that you need to make some, for any given, if it's odd or even function, for any given n, for odd n's you have the even solutions, for even n's you have these odd solutions, so you can find out the normalization constants a and b just integrating, because outside the box your wave function is 0. Integrating inside the box the function, you need to have 100% probability of finding the particle, so you'll find out what are these constants apart from a phase factor, perhaps. All right, you could find out some general phase factor for each solution, but the modulus of this value will be properly defined. All right, and of course, if you are calculating some of these functions as a function of time, some any of these functions, this will only change by a phase factor which corresponds to minus I, the energy eigenvalue times t divided by the h bar. All right, so that's it as a function of time. No problem with that. So look at these solutions here. The energies grows grow at the n squared rate, and you find out something like this. Remember, the first solution, the lowest level is n equals to 1, which corresponds to a1 equals to e0. The n equals to number 2 corresponds to the second energy level. It is 4 times the e0 in n equals to 3 corresponds to 9 e0, and you need to remember that this just sets the energy scale. It's h bar squared, pi squared, twice the mass divided by twice the mass and the length of the box squared. All right, and if you inside the box produce the modulus or the wave functions, to be precise, remember this, apart from some amplitude which must be determined by normalization aspects, this first solution corresponds, psi1 is proportional to cosine of pi x divided by a. From a over 2 to minus a over 2, you'll find out in energy scale here a first energy level corresponding to E0. All right, this is the energy of the first level. And if you look at this solution here, it has a maximum at the center and is 0 at the borders of the wall, or at the walls. All right, if you look at the second solution, is an odd function which is sine twice pi times x divided by a. It's an odd solution. It will have the following form. It has a higher energy. Energy is 4 times E0, and you'll have something like this here. All right, this is the second solution in the potential well. The third solution, you will find an even function. The fourth solution, you'll find out an odd solution, and the solutions are intercalated between one even, odd, even, odd, even, odd, even, odd. This is the sequence, all right? And it grows as n squared, all right? Well, this can be just thought as a one-dimensional atom, It has energy eigenvalues which are quantized, all right? And there are only one, apart from spin, you could think about spin also, so there is another quantum number, but in one dimension, you would have the principal quantum number of this pseudo atom and the spin value, which I'll call sigma. All right, so you have the principal quantum number and the spin, two quantum numbers. All right, if you go to three dimensions, what do you expect? In three space dimensions, you'll have the principal quantum numbers, a second quantum number which corresponds to the orbital quantum number, a magnetic quantum number, and spin. All right. So you have four quantum numbers, including spin. But why is four quantum numbers? Because apart from spin, you have three dimensions in space. So you could also find numbers, quantum numbers, depending on the symmetry. These are spherical symmetries in atoms. But if you have a cube, which corresponds to a very good approximation for quantum dots in many scenarios, you will find nx, ny, and z. So there are three quantum numbers and the spin, of course, of the particle. All right, so just because you have one dimension, the quantum number, the principal quantum number is n, and there are the spin quantum number, but there are no other quantum number associated here. But if you go to more dimensions, you will include more things like that. So this is just like a string oscillating or vibrating, the modes of a string vibrating. Right? This is the first mode, the second mode, and so on and so forth. And if you have more dimensions, you need to use boundary conditions at the other dimensions, and you'll find something like products of cosine of nx pi over a times, perhaps in more dimensions you have independent boundary conditions for the dimensions, sine of ny y divided by some b, not necessarily is a cube, it can be any volume in space. So dimension of the box is a over the x-axis, it can be b over the y-axis, and also you could have a z component. Also, you could have a cosine of nz times z times some c constant here, which is the dimension of your dot, of your supposedly quantum dot, z, and you will find out three quantum numbers. The combinations of these numbers will give you a set of energy eigenvalues and a set of energy levels. All right. So our infinite well is just a pseudo unidimensional atom. Of course, the potential is easy to solve, all right, and does not resemble in any way the potentials provided by Coulomb interactions, all right? So do not go too much further with these analogies. It's just to look at the quantum numbers needed to represent the system and the fact that the energy is now quantized inside the box. If you have a finite box, a finite quantum well, you you'll find out that the bounded states, which have energies below the U naught, which is the top of the well, are will appear in a finite number. All right. So if you have a box like this, okay, this is X, this is U naught, this is the potential profile. It could be made symmetrized also, all right? But this is finite. You will not have an infinite set of solutions. You have a finite number of solutions inside the well, all right? So you have a first energy level, a second energy level, a third energy level, and no more bounded states, because the energy of the next level would be higher than u naught, and in this case the particle is not bounded anymore. It can live outside. It's just the analogous of ionizing your atom in 3 dimensions. But just remember, for hydrogen atom is 3 dimensions. It has spherical symmetry. There are 4 quantum numbers designating the orbitals, and the energies are approximately given by the principal quantum numbers. There are corrections, but they are approximately given by some constant E0 for the atom, which depends on the atom. For hydrogen, this constant corresponds to 13.6 electron volts. All right, but is divided by the principal quantum number squared. Notice the difference here, because in our square well, the energies of the nth level is some constant, which depends on the dimensions of your well, right? Which is A, but is multiplied by n squared. So while in 3 dimensions for a Coulombic potential, right, the energies becomes less separated as you go to higher n values, right? The energy is, this is the 1s orbital, 2s, and the second 2p orbitals also. But as you move to higher n values for the hydrogen, in general for atoms, the separation of levels become less than the separation between the first levels of the atom. In this case here, the energy separations becomes higher and higher for an infinite well, because it goes for infinite well, it goes like En equals to some E0 n squared. Notice the difference here. 1 over n squared here, proportional to n squared. So the energy difference between levels becomes higher in 1 dimension. But this is just a weak analogy, all right? It's just for you to notice that in quantum mechanics, the energy levels becomes quantized. The solutions have to satisfy some boundary conditions, right? And bounded states are states which are more or less localized in space, right? Because they exist only inside some region and vanishes fast enough at infinity, all right? But coming back to 1 dimension, if you have a finite well, and this is a finite well which is not too small in height here, if u0 or u naught is not so small compared to some energy scale, which I will borrow from the infinite case, from h bar squared, y squared, twice mass a squared. If u naught is larger, much larger than this E0, which sets the energy scale for your problem, you'll have many bound states, a large number of bound states, and mainly the first levels, the most uh, the, the, the lowest energy levels, to be precise, will resemble your infinite well solution. All right. So even if it's a finite well, the first states, the evanescent part of the wave is decaying really fast, and you can approximate your first state by the infinite well solutions. All right. But if you go at higher levels, this evanescent part is important, and the solution differs from the infinite well. All right. Well, it's a very interesting problem, and you could now consider two wells, something like this. This is a very interesting problem in quantum mechanics. I will not do that here, right? But you could do that. You could do that, and it could just explain, for instance, the two possible levels of a molecule, right? It's very rough approximation for electron to go closer to some of the atoms in a molecule, and or can tunnel through some potential barrier, which could have some u naught value, and this could model a something like a molecule. All right. So or or tunneling between two states. All right. This could be used. So it's a combination of two wells. When they get in touch, the barrier diminishes in between here, but is higher than some levels here. And now you can see, when you approximate two atoms, making some analogies, that the higher the energy levels, which corresponds to the valence layer, the valence states, the higher the probability of the wave functions overlap, because the most profound states in the wells doesn't have any evanescent part for the wave. But as you go to the top, of your wells, the evanescent part is larger, and the wave functions can see each other there, and there are probabilities for the electron at higher states to tunnel from one side to the other, and you will find some molecular orbitals there. And that's why these states do not communicate with each other. They remain almost fixed. They cannot see anything happening. But the higher states, the outer shells of an atom, because the waves are more spread throughout space, will see each other, and they will interact and will form your molecular orbitals, right? To finish, just to finish our discussions, suppose that you have your infinite well, you have your energy levels, so E1, E2, E3, and so on and so forth. So the nth value corresponds to E0 n squared. In this value here, some sets your energy scale, of course, right? The applications for this kind of problem, for a square well, for instance, you can model as a very simple level structures being in practice, being constructed, being built for doing lasers, for instance, or if you restrict to more restrict your particle in more dimensions, you can find some quantum dots, of course. All right, so there are applications for this problem in the real world, and for lasers and using quantum wells or quantum dots. What you want to find is the quantization of levels, and levels being very clean. All right, but that's an application. But coming back here, if you consider this thing here, the infinite quantum well, you have a solution for this problem, and you insert a perturbation. So you have a delta of u, which corresponds to some, suppose, an electric charge, some electric field. I'll call this an electric potential V, suppose, right? Just potential energy, and times the distance. All right, this is just divided by A here, so you have an electric potential of amplitude V divided by A. It's just like constructing some capacitor there, and you have a electric dipole interaction. All right, in one dimension, it's more difficult to see this perhaps occurring, but suppose it emulates a perturbation which corresponds to the electric dipole, which is the more important, the dominant effect when you apply an electric field to an atom. The electric dipole dominates. All right, this is the more important effect. It will tend to distort the atom. It will mix the states. All right, but now if you have some perturbation like this, some delta u, call it delta u, the Hamiltonian now corresponds to the previous Hamiltonian plus this perturbation. And if you want to calculate the transition amplitudes between states, you'll have to find out integrals. I will not go into details, but the most important details I will talk about here. So the transitions are proportional to some m level times the perturbation here times the other level. For the sake of correctness, it's the complex conjugate here integrated over dx. All right, the transition amplitude corresponds to some matrix components, and this is what you find out from minus infinity to infinity, but in this case from minus a over 2 to a over 2, which corresponds to the inside region where the functions are non-vanishing. And in this case, you have something like the following. It's proportional to an integral of some constant here, which is proportional. Again, I will drop out this constant. You have a complex conjugate of some function here times x times psi of n dx. M and n can be chosen between the integers 1, 2, 3, 4, and so on. All right, but notice that this integral has symmetric limits. It has symmetric limits. And in this case, if you choose here an even value for n and an even value for m, which corresponds to odd functions, the same parity of the functions between these two levels, suppose n equals to 2, n equals to 2, you will have a same parity for the functions, but this x here will reverse the parity of the thing. So remember, even times even or odd times odd, they are even solutions. While odd times even or even times odd, you'll get an odd function, all right? And odd functions integrated over a symmetric interval, the integral vanishes, all right? So you have found here something which in quantum mechanics, when trying to explain molecules or atoms, is called selection rules, all right? Selection rules, right? Selection rules here means that by electric dipole interaction, which corresponds to something, some potential energy proportional to the distance, you'll find that an even state is connected only to an odd state. So your electron can jump from here, from an even state to an odd state, but it cannot jump right to another even state. Or it can jump from an odd state to an even state, but it cannot jump from an odd state to another odd state. Why is that? Because if this is odd and this is odd, you have odd times odd, which is even, but x is an odd function. Why is that? Because if you reverse sign of x, this integral reverses sign. This is the concept of even and odd functions. If you reverse sign of the variable, you reverse sign of the function. And x, of course, is odd, because if you change sign of x, it becomes minus x. All right, so this function is, of course, odd. It's just a straight line. It's just a linear function, but it's odd, of course. Then you need to multiply an odd function by an even function to get an odd. And now you need to multiply by an odd function to get the integrand even, all right? So this integrand here results in a finite value for the integral, which is non-zero, only if you choose n even, n odd, or n odd, m even. Otherwise, you'll get a vanishing result, a zero. All right? This is a selection rule. You cannot produce a transition from the fundamental state to the third state by an electric dipole interaction. But you can produce a transition from the fundamental state to the second state, the first excited state, or from the first excited state to the fundamental level. Both ways, all right? Also, you cannot produce transitions from the second state to the fourth state because they are both odd functions. But you can produce a transition from the second to the third state because they have opposite parities. All right? This is a selection rule. In an atom, this also occurs. Electric dipole moments will not allow you to pick an electron in the 1s orbital in a hydrogen atom and make a transition to the 2s orbital by electric dipole interactions, because it's forbidden by selection rules. And also in 3 dimensions, you will find out that the atomic orbitals have definite parity. S orbitals are even functions relative to inversion. P orbitals are odd. D orbitals are even. F orbitals are odd, and it goes on. So the main ideas which can be drawn, the conclusions which can be drawn from these one-dimensional problems, which corresponds to energy quantization and all that, and the selection rules, you can, with certain care of things, you can generalize to 3 dimensions, to atoms and to molecules and all that. All right? Well, I'm finishing here. Next time we'll talk about the harmonic oscillator. Bye bye.